Hi everyone, and it's great to be back. And so today I'm going to show you a few things that we've been doing since my last talk 2 years ago, but mainly I wanted to not give you a terribly technical talk. I know the expertise goes from deep experts to aficionados. And I wanted just to give you a bit of perspective of what we're currently thinking about doing and are currently doing. So very recently we published this paper called The Artificial Intelligence Clinician in Nature Medicine, and I'm going to talk a bit about that because that created a bit of a stir. But I wanted to bring you back to the real idea of what it means to have intelligence. And to have intelligence, I'm sure we can all agree that we sort of need brains to do that. And maybe we can start with a very simple questions. Why do we have brains? So if you think about all the organisms on this planet, you will find that a good chunk of them, the trees, the flowers, the grasses, and so forth, the corals, don't really have a brain, and they don't need a brain. But there's a different type of organism, and that's called an animal. And effectively, everything that has a muscle that can move may have a brain. But you will not find something that has a brain and cannot move. Okay, so that's an important thing to realize. So there's something very closely tied to the ability to act, interfere, change the surrounding world through movement that makes it sort of a good idea to have a brain. But nothing in nature has a brain that doesn't move. Having started with that, perhaps we're slowly coming to the point what I'm talking about here. It's what we call human in the loop. So there's some form of loop. So what is this loop about? This is, if you are a computational neuroscientist, like half my lab is, then we call that the perception action loop. The fact that to be able to make intelligent behavior, like playing volleyball, there's a whole set of biology that processes the sensory information, learns and adapts from it, and then generates some form of muscle actions that then output in behavior. And of course, the fallacy of historical neuroscience was to cut open this loop and show a stimulus and measure a response. That's sort of the boring neuroscience. But the real excitement comes when you're realizing that perception and action are closed loop. They're constantly affecting each other. In fact, if you observe your eyes, they're constantly in motion. Their motion directs what input you're taking into your brain and what information you have available to make decisions. Right? So this loop is very tightly coupled. And so when we're talking about artificial intelligence, I find it very difficult to not think about this loop. So if you're talking about perception action loops, hey, what's going on here? When you're talking about perception action loops in engineering or computer science, we have typically something that we call an agent that chooses an action and that affects somehow the world, and then that action has some feedback that is again perceived from the agent. So if you have to predict the best action from some feedback, classical engineers call that control theory. If you have to predict feedback from feedback, so what's the stock price of tomorrow going to look at based on the stock price of today, then we call that time series analysis, autoregression. If in all of this you have little knowledge of the world because you want to learn, then you can learn from actions and feedback to predict the feedback. So that's state estimation, Kalman filtering, SLAM, and so forth. And you can talk about learning from actions and feedback to predict future best actions. And that's in the domain of reinforcement learning. Okay? So that's a basic view that we subscribe to. And the interesting thing is now, if we know what the actions of an agent are and what sensory feedback flows back into the agent, how good can we reconstruct the agent in our thing? It's of course a brain, some form of thinking element, what the whole agent does if we know what action the agent does and what feedback the agent gets. So over the past 10 years, we collected this type of data. Crazy effort of trying to collect roughly 80% of all the movement output of the brain. So people get to wear this the whole day. We collect every single finger movement. You see the reconstruction of the fingers here in real time, the reconstruction of the skeleton. This is how this gentleman is sitting here. And you see the gaze vector, so how deep and where his eyes are looking, sticking out here. We, of course, also see what this gentleman is seeing. and specifically also where his eyes are jumping around, what he pays attention to. Okay? So that's estimated. We have also the audio. I spare you the audio. We estimate that this is around 70 to 80% of all sensory primary inputs that we can collect. We don't get touch at the moment, but we're working on that. But that's a good amount of the input into your brain and a good amount of the output of your brain. So if I just collect enough data, the idea is I can do something called system identification and basically fit a nonlinear memory function that basically maps from input to output. If you collect just enough data of yourself, then probably you can generate a fairly good simulation of you. That's at least the idea. So we can apply that, and we have done that, to reverse engineer what we call manual expertise. So we focus this specifically in the domain of hands. And so one of the things that came out of this type of analysis is that we discovered that certain hand movements that everyone thinks are important are actually not occurring in daily life. Specifically, the precision pincer grip, which every prosthetic has, which all robot hands can reproduce, which your stroke therapist will rehab you on, and what your hand surgeon will try to preserve if you had an accident in your hand. Issue is, this thing virtually does not occur at all in our daily lives of modern Imperial graduate students who do these experiments. So we live in a day and age where we actually don't know quantitatively what your output is, what your actions are, but at the same time you can get, from various companies, I'm not making the names, your genome sequence for $2.99. Right? How is that we don't know something as fundamental as behavior? So once we started asking questions like that, we realized, if we really want to study hand movements, most of the hand movements that are interesting are not grasps. Every monkey grasps. All robotics does grasping. But actually, what makes us special is object manipulation. Interactions within an object being able to do these type of things. Monkeys don't really do that. They manipulate the whole object while holding it. But what makes us really human is the ability for in-hand tool and object manipulation. So at a recent conference in IROS, I gave a talk where I said, let's stop doing monkey robotics, let's start doing human robotics. And this is just an example of work that we started where we're trying to find ways, learn, design new robotic hands, but also how to control them so that we can perform proper in-hand object manipulation. They're not made for grasping, and if you have a supermarket to stock, I wouldn't use this specific hand, but this specific hand gives us in-hand object manipulation capabilities, and we can learn this from these large data sets. And again, I challenge everyone, I buy you a beer, if you find me videos of robotic hands out there that can perform true in-hand object manipulations such as texting, right? They're all optimized for grasping. In other domains, of course, eyes, eye movements, constantly in motion. From the social setting you just came out from, probably you're particularly good at predicting intentions of people while you interact with them in the cocktail party from how they're looking at you in the environment, right? We're all quite good at trying to pick that up. And so this is information flowing out about your future intentions just from the eye perspective. So the first thing we can do is we can, for example, try to predict where you're looking based on your actions. So what you're seeing here is a short video. You see one dot that jumps around a lot. That's the human eye of the person currently performing this task. And the other little dot is a continuously prediction of where we believe this person is looking. Okay? But we don't do computer vision. This algorithm is completely blind to the scene. We are predicting where this person is looking simply based on the movements of the body, right? So that's a fairly good prediction. It beats other standards. You can read about it in our upcoming papers. And this allows us then to develop robotic technology that decodes your movement intentions from how you're looking at stuff. So Sabine here is eating and drinking with her two arms. At the same time, she's imagining painting an oil painting, and that's generate eye movements that we can decode and make a robot execute that. So be clear, the robot is not pre-programmed. It's streaming, decoding how Sabine is looking at this painting, and then basically painting this painting. Okay, so that's cool, and that's decoding. And if you think about what a lot of machine learning and AI at the moment is about, of course we know there's a lot more to it, is effectively what I call perceptual artificial intelligence. So you have some form of system, equipment, environment, or business that gives you situation and information feedback. You have some form of decision maker, be that a worker who needs to think about how to control stuff, that's many serial decisions, or a manager, and then they basically output based on that a single decision. That's open loop. Yeah? That's what you do. And of course, if you do machine learning, you know this is what we call supervised learning. Finding a mapping between input and output. If it's continuous, it's regression. If it's discrete, it's classification. If you look at single decision, it's decision making. And of course, here again, there's a whole family of algorithms, and I really don't know what's going on here, that have been developed over the years, but basically all of this has been taken over by deep learning at the moment. Now, there are, of course, other methods, data efficient methods and so forth, but that's where a lot of the interest is, and there's a lot of hype about that. So, speaking of hype, perhaps, and here I'm just digressing, let's look at the Gartner hype curve for last year. So, as you know, Gartner believes all technologies follow a certain cycle that follows this hype curve from some crazy professor coming up with something, some hype being generated, some form of peak of inflated expectations, the trough of disillusionments where most technologies die or are resurrected 3 times in my life now for virtual reality and 3D TV. But okay, they're coming then slowly up, and some of them slowly make it to the plateau of productivity. And I've been looking at that since many years ago. I was working for McKinsey, and I've been clearly looking at what are the emergent technologies. What we're finding at the moment is this unique concentration of roughly 2/3 of all emerging technologies being solely out of the area of AI, machine learning, whatever you want to call it. That's a very striking level of concentration. Most of this, is my belief, is driven by the perception in public of artificial intelligence being successful. And that's what I call the AI iceberg. If you look at what actually drives public perception of AI, there are currently tangible manifestations of artificial intelligence, such as, having your chat with your phone or hearing about self-driving cars killing people, that gives you a feeling that AI is out there and you can touch them. And that's just, the peak of it. The vast majority of machine learning applications are already deployed and in play, and most of people don't realize that. But it's these things at the top that interestingly also capture something about a perception-action loop, an interaction. Something comes back to you that really is driving public perception. Okay? So that's very interesting. So perceptual artificial intelligence that recreates perceptual abilities of humans, is really driving a lot of this. And McKinsey in 2018 made an estimate of the value of the deployment of supervised learning. This is a bunch of people spending some time, probably quite smart, thinking about in a good way what's the value of this. And they're estimating that deployment of supervised learning sits at around $0.8 trillion if it's rolled out across all industries. So that's great. What other things are out there? Well, once we've started talking about unsupervised learning, we can talk about unsupervised learning, which is finding some form of structure, clustering, dimensionality reductions. And again, the same clever people went out and tried to estimate and put a number of this. They say it's slightly less valuable at $500 trillion. So what remains? Well, that's of course reinforcement learning. The idea that there's a system, an agent that acts, updates its perception, collects some rewards, and based on that finds an optimal decision-making strategy that for many different settings formulates the optimal actions. Right? And in this domain, we've seen fantastic successes, really driven by DeepMind. So I'm delighted about the next speaker coming from that stable, where you have seen a lot of work from Atari video game playing Go, and so forth. And interestingly, not surprisingly, it's really reinforcement learning that is the closest to capturing this perception-action loop of human intelligence. And for me, it's also the main pathway to achieve true general artificial intelligence is to crack the reinforcement learning problem. And interestingly, if you look at the estimate of optimization of decision-making processes and reinforcement learning that these gentlemen came up with, it sits at roughly $4.5 trillion. So that's 5 times as much as the benefits of supervised learning, or really 5 times the hype, if you want to think about that, that deep learning alone can do that. And I think deep reinforcement learning is, of course, here a very prominent effect. And it's quite interesting to see why and where this will play out. And forgive me for being very, MBA style here, but I think it's just really interesting to explore the consequences of this perception action loop. So this is a different study. This is data from Boston Consulting Group. Of course, these two consultancies are driving a lot of people, driven by a lot of C-level decision makers about what can we do. And here you see different sectors. Here you see the categories of work as they were clustered by these gentlemen and ladies. And here you can see the technical feasibility of replacing this with current technology from the machine learning AI end of things. And the interesting thing is, there is not a lot of blue around here, right? A lot of the technologies don't seem to be AI-able. And so what is the limit for that? So this is now data from the World Economic Forum, and it's another McKinsey study, which basically says the critical limit is the predictability of a task, not just of a single action, to be able to replace that. So for example, predictable physical work like machining over and over the same piece has a very high replaceability, and unpredictable physical work like this gentleman who's cutting trees has a very low probability of being replaced. Okay? So that just drives back the economic message of thinking things through in closed loop. So let's think about this now a bit further. So what is AI that is beyond perception? So what is really the challenge of most jobs is not just recognizing a situation, but then dealing with the situation. Of course, not just dealing with a single situation, but managing a whole project. That's why project managers are always very welcome. And that's, of course, nothing else but basically closing the loop between situation and feedback and decision and actions and whatever your equipment, environment, or business needs. And the interesting thing about this is that these processes often emit data. So whenever you're generating data about your decision and that is stored in a usable way, that's great. And whenever we have information about your situation, that is great. And so we try to apply that idea of machine learning in medicine. So if you think about AI in medicine, then you find that all current AI in medicine excels at perceptual tasks. So there's very nice work of skin sensor detection from photos, achieving superhuman performance, recognizing, for example, head traumas, or have some form of new digital biomarkers. This is something I spoke recently about to rapidly accelerate clinical trials. So all of these are perceptual tasks, the ability of someone to spot or monitor something. And of course, when you're going to a doctor, you just don't want a diagnosis. You want treatment. And what is treatment? Treatment is trying to help you by some form of action, observing how you react to that, closing the loop, then again, adjusting maybe your treatment or continuing with that, and then eventually weaning you off whatever treatment you're getting to then. It's closing the loop. So we looked at this problem by what we called autonomous treatment. So a bunch of years ago, and we were not the first ones, I have to say. So the first models was by Damien Eretz and Gibert Stan, who applied the idea of treating HIV optimally by applying a reinforcement learning model. So they defined a dynamical set of equations, ran that in closed loop, and then of how HIV and some form of treatment interacted, and then basically controlled the system with reinforcement learner. And similar work was done also in dialysis. So when I basically set up the lab, I realized, okay, we can't just do that in silico, let's do that in vivo. So we actually then set up a whole set of trials where we wanted to apply that to a simple problem where it's easy to measure the state of the patient. In this case, it's diabetic patients where they have an issue with controlling blood glucose levels, and there's a simple action, that's the amount of insulin we deliver. And basically, we had patients, I should say, we've done this first on rats with a clinical partner, and then we can talk about how to do that in patients. But basically, there was a pump that was implanted, and delivers you with insulin. There's some form of sensor that measures what your blood glucose level is. There's some form of technology that then decides what to do. So these technology exists. You can just buy them. If you're diabetic, you may have them already. But the important thing is that you still have to press, yes, I want that. Of course, your brain and your autonomous nervous system do that for you. You know, you eat a cake, it already predicts that you're going to have a sugar rush, and it starts releasing insulin. So the interesting thing is, of course, the typical diabetic patients, shoot themselves up with a large dose before or after a meal. And when we let this system run closed loop, what we discovered was the following thing, that this blue line is the blood glucose level in one of these creatures, and the animals, and the black line is the insulin injection by the system. And the system found a solution where the cost function for this reinforcement learner was specified in such a way that we want to keep as tight as possible the blood glucose level to be normoglycemic, and at the same time minimize the total use of insulin so that this implantable pump lasts for a long time. And interestingly, you can see this, I wouldn't call it a fractal pattern, but a very different pattern from how people inject themselves. Basically, the system injects always a bit of insulin to keep the system on edge. And then basically, when there's a large shoot up in insulin, in blood glucose levels, the system does not have to deliver so much. So it keeps the system at a level of critical instability. Good. So that's a closed loop system where we can close the loop and measure that in patients directly. But in many other settings, such as the settings I described about the cognitive AIs, you have situations where you really can't run this in closed loop in detail, or you need to be very careful, and sort of you need to bootstrap the learning at some point. So this is where looking for sources, where do we have loads of high-quality data about the state and about the action of people, we ended up in the intensive care unit. That's an intensive care unit. And as you see from all the beautiful movies that are out there, there's tons of data being generated, like just gigabytes flowing out, your heart rate, your blood pressure, your blood tests. And thank God for the NHS and its regulations, every single decision by a nurse or a doctor needs to be recorded, right? In case of this lawsuit, but just also for reporting purposes. And because free from text is not a good idea, it's digitally entered. So this means we have now access, and we discovered pathways to access of data where we have high-resolution physiological state of people, 65 vital signals collected from people, and we have actions. And now the question is, what do we apply to an intensive care unit? And so here, you may have heard about sepsis. It's the third biggest killer in the US overall. It costs the lives of 250,000 people per year. It's the main cause of death if you're in intensive care. And it's one of the most expensive medical conditions hospital, costing us $25 billion. And that's because sepsis is sort of a diffuse infection that you're having, but that's not what's killing you. What's killing you is that your circulatory system breaks down. And if that breaks down, nothing else helps. So antibiotics are not the main, are basically what are taking away the sepsis if it works, but you need to live long enough. And so here, clinicians basically have two knobs that they can turn to prop up your circulation. That's, the IV fluids, the drips, and some form of drug that we call vasopressors that make your blood vessels narrower. So I can pump up your blood pressure by pumping you full with liquid or by making every vessel shorter. And people just don't know how to manage that. There are many studies, many trials how to do that. And at the same time, it's a very diffuse condition. You don't know really how to help people. So this is where we came up with this idea of the AI clinician. So we take the clinical decision-making data, we observe the decisions and its impact on the patients, and we try to structure and analyze that. And again, forgive me for those that are bored by these simple so-called grid worlds, but basically the idea of the system is, you arrive in an intensive care unit for whatever reason, and then you contract sepsis, and we want to manage that you're released and don't die. Okay? So what it means is every single box here is a state of your health system, and you cannot go into certain states because physiology does not allow that, so not all paths are possible. And now the question is, how do I get from here to here? So the one obvious path is, you choose the shortest path in some way, assuming that you can spot the shortest path, and assume that you can define a state. So what we then did is we used various forms of dimensionality reduction. In this case, to basically try to cluster data from patients, and we had access to two databases, a database of roughly 30,000 patients and a second database of 3 million patients. And we used the small database to build the model, and when we tested the model on the larger database of 3 million patients. In the end, we used fewer than these 3 million patients because people needed to be sorted out because they had other conditions or and other factors, but we just focused on patients who had sepsis and were dying from them. So, applying standard unsupervised learning gives you various forms of clustering the data. We can go into the details of how to do that optimally and in a data efficient way, but effectively we could identify, we find that the optimal density of states was around 600 to 800 states. Okay, we tried it with 2,000 states and more or less, but basically the very different algorithm converged across this optimum. So this means each circle is now one of these guys, and it means that if you're ending up in the ICU, you have a certain journey. You may, for example, and here I need to look at this screen because I can't see so well, so you start here, and then this patient jumps around across these states till the patient is released and is healthy, and this patient is not so lucky, so this patient enters here, jumps around in states, and then eventually dies. Okay? Just so you know, from any of these states you can be released, and from any of these states you can die, and basically the color coding gives you the mortality probability of dying or living in the state, just showing you that there's some form of structuring. And so what we can then extract is basically trace the journey of the patient's life or death as a continuum of probabilities that go up or down for dying. That alone would be a useful signal. But of course, when we do reinforcement learning, what we can do is we can calculate what is the optimal, not single decision. So for example, if you're here, the best decision may be, oh, let's steer you as quickly as possible here and drive you up and then to the right. That may work. But for example, you may not know that certain paths are not possible. Simply, it's not possible to do that. So a naive solution would be, oh, I don't know, something is failing, let's give you more of the drug for that, and I drive you into the dead end. Okay? And that actually is a challenge that many junior doctors face because they know, oh, this value should be higher. Oh, what do I have to do to improve that? And that leads into some short circuits. Of course, the approach of dynamic programming and on reinforcement learning more in general is then to basically work backwards effectively from the solution and find the optimal pathway. So in this case, you wouldn't even think about going in that state, and if you were here, you would go down, and then you would steer up and clear of death. Okay, so that's in a nutshell the idea. So this is what we then did. So we took the data, basically looked at, defined the patient states, then defined the typical dosage with which clinicians dose these two type of drugs, the vasopressors and the IV fluids. And then cheekily, I have to say, we simply defined if the patient dies after 90 days, you get minus 100 reward. And if you're still alive after 100 days, you get plus 100 reward. Okay? And then you just do box standard reinforcement learning that you can take from any introductory class. And then we validated this on this database called Mimic3. And then we run this on a second database, the EICU database. So what you get out of this is you observe a system that makes actions. You look over their shoulder, so it's off-focusing learning. But now, and you have to be very careful, this is not a closed loop system, right? We have not actually drugged and dosed some patients with it. We just observed what the clinicians were doing and built out of that predictive model of the transition probabilities and the reward functions and so forth. And then we look at how we can then estimate value of states and make them decisions. Okay? But it's not as simple as simply measuring the empirical transition probabilities, because, for example, you may decide on making different decisions than the decisions that the actual clinicians took. So now you have a mismatch in the probability distributions, for example, of the actions that were chosen by the real-world clinicians and the optimal actions that you may have computed, and you need to attend, for example, you need to factor that in the sampling methods that allow you to shift one distribution into another distribution and account for that. And there are loads of these rather technical statistics of machine learning tricks that I'm not boring you with, but you can have a look at in the paper. We have a very long methods section that explains how we did some of these testing and developments. But basically, I want to show you here a slice of how good this system performs. So, this is basically, I'm plotting the following thing. So remember, we are looking at every single decision a clinician made for every single state a patient was in. Yeah, so sometimes there were multiple patients in the same state and multiple clinicians making decisions, and these affected these patients then down the line in some way or another. Okay? So now imagine, in some situations, one clinician is much better for that specific setting at making a decision than another clinician. Or it may be that a clinician makes a mistake, but that turns out to be a good mistake. So everything that we've ever seen were decisions made by real clinicians. So it's not going to be crazy stuff we pursue. And it also means that all that our system will ever do is play back decisions that actual clinicians have done. We're just basically finding the optimum for the overall. So what I'm plotting here is the average dose of, in this case, this vasopressor drug, and this is the average dose of the intravenous fluid. If we're at 0, this means that what our optimal policy, so the AI clinician chose, and what the clinician gave, or mapped on top of each other. If there was a difference, so if the clinician gives more than the AI, then the data goes here, and if the clinician goes down here, then he's given less, or she is given less. And similarly here, if you give more or less. And this is our best bootstrap estimates of the uncertainty we have. The important thing to note is, so if the clinicians coincided with the decisions of the AI system, the AI clinician, then the actual mortality of that patient was lowest. So we're predicting the mortality not because you had certain physiological states, but because you had certain physiological state and a specific sequence of treatment was applied. So here we find a very strong optimality, and so if you follow this AI clinician, that's very good. And here, on one side, we found that it really gets worse, and here you have to go really to the edge to see that the mortality goes up. And so then some colleagues came and said, hey, Aldo, your thing is not working at all because I can give you a liter less of IV fluids, and I'm really not improving your survival. And then we were like, oh yeah, okay, what can we do about that? So then, of course, you do this work together with clinicians, and the senior colleague said, well, this is very well known. There's something called the random study, capital random, that was done 10 years ago, where people were dosed with 1.2 liters less than was typically recommended, and there was no difference on survival. That was a specific clinical trial. You can read it up in the New England Journal. The interesting thing is, we didn't need to run a specific clinical trial. We got this non-dependence over this broad range up to a liter out of routine clinical data. So I'm all for evidence-based medicine and the need for random controlled trials. But just imagine the system, and I didn't know about this when we coded this up, right? Extracted that out of the natural patient data. That's quite interesting. Good. We can then look at other things. For example, we can, explainable AI, everyone wants an explanation. We can then look what are the key drivers of the features, and this is a very high-dimensional state vector you can imagine that drives all the ICU feeds, that drives the decisions of the clinician, of the AI system, versus that of the average clinician's policy, and there are quite some different numbers. What strikes us, for example, here is the topmost entry that the clinicians seem to pay a lot of attention, and it may be as simple as a specific textbook line prompting a lot of people to look for that specifically. The interesting thing about this system is it's extremely dumb. It knows nothing about physiology, it knows nothing about medicine, it knows nothing about humans, it doesn't know even whether the person had basically a car crash or heart surgery, why they're really in ICU. But, and this is a very interesting point to consider, a typical senior consultant, when they retire in intensive care, will in their lifetime have seen 12,000 patients. And that's a lot of experience. Junior doctors start at 1, right? And then they build their experience up. This system has potentially started with multiple lifetime experiences of just pure data. So it raises the question, at what point is the amount of data so overwhelming, many lifetimes, that you don't actually need to understand medicine or physiology or these details, and at what level can this system start to help. Okay. And it's interesting because maybe that number is not as high as I personally would have predicted initially, to be confirmed with that. The other thing is, clinicians treat patients individually. They look at you, how your mood is, how everything is affecting you, how pale your cheeks are, and so forth. But we run this algorithm many, many times with many different numbers of states. So that was the condition we optimized, not just the local clustering, the fit of the clustering, but what gives us the highest, best policy for survival, right? And we found that this number of under 1,000 states is really good. It gives us the best policy. Again, to be verified in real trials. But does it really mean that a clinician does not distinguish in intensive care more than 600 different discrete states of a human? That's a challenge. It sounds a bit little, right? I want to be a bit more individually treated. But then you realize, how much time does actually a clinician have to spend to interact with an individual patient when they're on the ward? I think you're lucky if your GP gives you more than 10 minutes. So think about how many bits of information can a clinician absorb per minute in a given clinical setting. That's finite, right? And so clearly the ability to distinguish between different types of patients is limited by the amount of information they can absorb given current facilities. And so maybe the fact that 650 states are fairly little, maybe that's simply limited by the finite information capacity of patients, of clinicians. So, in terms of this type of work, how am I doing for time? 36 minutes, right? I have a few more minutes. Yeah, so in this type of work, the next step is very clear. We want to take this into the intensive care unit. This is work where the intensive care clinicians are very keen on because they have all these data feeds. They know that this data is out from, and they're really pulling it much more forward. So our idea is not to have an autonomous clinician, but to have a system that prompts nurses and the clinicians with what the system thinks are optimal actions. They then can approve it or do something else, and we learn why they're doing something else. And that's currently we're trying to roll out in the Imperial College Healthcare Trust. Of course, if you can give me patient data, and if you can give me clinical decisions in a digital format, we can technically roll that out in any other domain of healthcare. Which brings me, and I'm concluding slowly here, to the idea is, can we apply this, of course, in other settings, right? Remember where we started with the guy eating breakfast. So sometimes things happen to be lucky. So imagine you want to see what does a world-class driver do. So in this case, we have the world champion in Formula E, who agreed to be filmed in an Audi R8 Plus, putting all the tech that we have, all the movements of the hands, all the movements of the feet, everything that he sees, and all the eye tracking, on the Top Gear racetrack on a November day at 0 degrees, centigrade. So it was frozen. And we asked him, please never drive under 60 miles per hour. So we wanted to explore what happens when people are in extreme situations. And so here's an application to that, obviously, is when we can study this perceptual input, and some people recognize themselves in this slide, and the motor output, we can take a system such as the Carla VR simulator or 3D simulator for self-driving cars that's currently deployed by many self-driving car deep reinforcement learning people, and hook that up with a system that can give us input of what people are seeing, measure the eye movements, measure the body movements. For example, with the video game setup, we can start exploring how to augment machine-based, simulation-based reinforcement learning with human data in those situations that just by experience, most reinforcement learner will never encounter, extreme driving situation. And then we can think about a theory on how to inject that and how to add to that, right? So that is the situation you don't want your self-driving car in traffic to be in, but we can take the human experts on how to do that and apply that there. Of course, the same thing we can also do with intensive care clinician. You know, we learn the standard model, we help people, and then we look how the pros are dealing with the really complicated cases. Good. So, what I've spoken to you about. So I really want to push this thing towards what I call human-in-the-loop AI, where the human is not replaced by the AI, but is part of the system, and it's a symbiosis. And the idea is, of course, that we want human control in these decisions. There are many things we need to talk about, what we've done here, but you need to think about how you can engineer and design the trust relationship of such a human, how you can be data efficient so it works for you, not just for the average person, how you can do it in a privacy-preserving way, how it can be interpretable, and how you can be human-like. And with that, I want to highlight that at Imperial College, we have a rich machine learning and AI community. We call ourselves the Imperial College AI Networks. We have 78 professors in there, over 800 PhDs and postdocs. And once we formed this network last year, we discovered we're the largest AI institution, academic institution in Europe. And I just should end with this, with highlighting the people who have done all the work I've spoken about, the photographs here. So the lead on the AI clinician was Mathieu Komorowski, who very interestingly is a clinician who decided to do a PhD in artificial intelligence and reinforcement learning. And there are many other projects that do good stuff. Thank you.
Aldo, we've got time for 2 questions. I'll start things off. Aldo, thanks for the talk. So I guess reinforcement learning is a good match for problems where you have a delayed reward. In this case, the reward, or the opposite of the reward, was death. But did you do any comparisons with simpler systems that didn't use any delayed reward and that used some kind of intermediate outcome, some intermediate clinical outcome like blood pressure or something a bit simpler?
That's a very good question, and we got that question. And so if you look into the clinical statistics literature and their approaches there, is what people are very keen on in that community is what we call causal inference. So the idea is that there are certain treatments that you give, and there are certain effects that drive that. But what is the real cause, we may not know from the data. For example, if the tobacco tax rate goes up, cancer deaths go down. Does it mean that tax rate causes cancer? No. It means that that affects the consumption of cigarettes, which then drives the death rate. So if you just look at data like that, you will not be able to distinguish that. And so this approach, and there's very careful, smart thinking about how we can ensure and give bounds on that, has driven a lot of the clinical data aspects. And so there, the focus is really on the short-term actions and their immediate outcomes. What we're doing with the reinforcement learning approach is really look at the whole sequence of treatments and look at this long-term effect. We're basically expanding the horizon. What's very clear to me is that we need to do the causal inference nevertheless, because reinforcement learning causal inference communities are effectively orthogonal, not just academically speaking, but also paper-wise, right? And so, of course, there's something intermediate, the POMDP communities to do partially observable system, but there needs to be some form of fusion of the two if we want to do that in a meaningful way. And I think that goes back to us to what are the intermediate outcomes that really drive the long-term outcomes, or is everything just upon an optimal succession of smaller decisions?
Maybe related. So
You have a microphone in your seat. It's right next to you.
in that clinical setting, if you have a system, an AI system that's providing advice to a clinician to tweak one of 2 knobs to adjust the dosage, do you intend to provide some explanation for why the clinician should do something that's maybe different than they had in mind? And how do you generate the explanation of what they ought to do?
And that's a very good question. So now, this is of course recorded on YouTube. So there's a challenge that I find with the explainable AI communities. That community is interested in generating what computer scientists think is a good explanation for a non-expert or for an expert. The issue is, it's open loop. I don't think you can do any form of meaningful explainable AI if you're not evaluating the quality of the explanation at the level of the explainer. Is the explainer understanding the explanation? Is the person being explained to or explained at being convinced by that? And so there's a whole, let's call it computational neuroscience of trust and understandability that we need to be able to model, so when we can predict, if I give you this type of information, the features or whatever, that you're actually being convinced by that. And that may look very different for very different target audiences, right? So personally, showing this is not explainable, and it will not drive the trust of the user. What will drive the trust in the user, and we're doing some tests here with actual clinicians, is if I can basically predict on a short term what we think the effect of your action or the AI's action is, depending on what you choose to do, and then they get basically convinced, they see, oh yeah, the system predicted it correctly. Now the system is not built as a predictor, but how do you build trust? How do you trust someone? How do I get to trust you to do a decision together with me? From some form of relationship. And that's a different talk. I'm happy to give it another time, about how you do the closed loop in the explainability and the building of the trust.